So, all right, well, welcome to Applied Optimal Control. We'll do that one more time for good measure. All right, so anyway, who am I? I'm your instructor. I'm Christian Hubicki, okay? When it comes to so in general, if you want to know about me, I'm an associate professor of mechanical engineering here at Florida State University at the FAMU College of Engineering, okay? Also, I do have hobbies. This is me on a beach. In case you're curious why I'm doing a shoot for Entertainment Weekly, just Google it. You'll figure it out quickly enough. Okay, so that was on Entertainment Weekly yesterday. Whatever, we're done with that. So, syllabus. Syllabus is posted on the Canvas site, okay? It's actually up. You just go to the files page. It's there currently. It'll be more easily accessible soon, but you can go to the files page. The grading, we have 20% is quizzes. It says time quizzes. I'm going to get rid of the timing. There's no time limit on the quizzes. Canvas quizzes on the material. 45% of your grade is homework, okay? And about 4 to 5 assignments, and they are coding assignments. And that's a major part of the class. We will be doing a lot of coding in MATLAB. Most of you, all of you should have some experience in MATLAB, but we will do lots of coding examples in the class. And the other 35% is a final group project, okay? So we'll get to all these details in a bit. We will be grading the assignments, traditional grading. There are no traditional quizzes in the class, like in class. There are no traditional exams in the class, okay? That's the format of the course. Are we streaming yet? We're not streaming, okay. All right, we'll have to, after all that work. Okay, let's see. I'm going to try to restream here. Select stream. So it's just not starting.
It just is waiting for you.
Why would it wait for me? Okay, select stream, refresh. Okay, well, we're recording regardless. I'll put it up on YouTube after the fact. Okay, we'll get it on there. So, all right. So for the syllabus, so that's it for the syllabus, okay? Now, when it comes to the actual materials, okay, for prerequisites, you might have noticed you have a question.
You said there's going to be quizzes, but there's no traditional quizzes?
Yeah, like you're not sitting in class with like a piece of paper. That's what I mean to say. So the question is, so does that make that clear, Skipper? Cricket Skipper. Yes, Cricket. Yeah, thank you. So no traditional quiz. You're not sitting in class with a piece of paper. You're at home, and you should have as long as you need to actually do the quiz on Canvas. That make sense? Cool. So prerequisites are a bit vague for the class. You might have noticed there's not like a lot of traditional course listing. And basically, I try to keep my classes to be as open-end, as sort of open to folks as possible, assuming they have a few prerequisite skills. So one is I need people to know some calculus. And what I mean is you got to be able to take a derivative, okay? That's going to be very important for any kind of dynamic system. You have to be able to take a derivative. Now, that's an entry-level course in college, so you should be fine, okay? Linear algebra. You didn't necessarily have to take a linear algebra class, but you should be able to multiply matrices. And if you don't remember, there's a Wikipedia article, okay? And we'll do it enough times, you'll get some practice, okay? But that's what we're talking about by linear algebra. You don't need to know a lot about how to calculate span or how to do an eigenvalue by hand. Those kinds of linear algebra things are not a core part of the course, and whenever we cover them, we would actually recover them for you all. Coding. When I say you're coding, you don't have to be a master software engineer, okay? It's helpful to have some exposure to MATLAB, which many of you have, okay? Let's see, I don't know why it's not going here, which many of you have. And what I mean is you got to be able to write a loop, and you got to be able to assign variables. And anything else that we cover, we're going to cover in the class in our coding examples and tutorials. Now, just because these prerequisites are easy does not mean the class is easy, okay? It definitely, I would not call it an easy class. I don't think I've met anyone who, no, I'm sure some have. Some people called it an easy class. But what it's going to require, though, is a lot of persistence and debugging, okay? Just because you know how to write a code in a loop doesn't mean that programming is easy. You're going to be doing a lot of debugging, and that's going to be very important for the homework assignments. That's why they're such an important part of the class. So, all right, when it comes to next, so policies. I do want you to attend the lecture. And given the fact that I record every single lecture, I think it's actually even more important that you come. Now, because like what will often happen is people will take the class and they're like, oh, lectures are recorded. That's great. I can sleep in, watch it later. That is dangerous. That is dangerous, all right? So often that just like leads people getting just like, oh, I missed this lecture, I'll catch up on it later, and it just cascades, okay? So I do want you to attend in person. There is an attendance policy in the syllabus. There are course excused absences, okay? We'll talk about Zoom lectures, because there are some Zoom lectures. And you can turn on webcams if you want. Whatever you want to do, it's fine. I'll take that down. Policies, you can't copy each other's work. You can work together, you can't copy each other's work. That's going to be, don't make me go and check if code is copied. I'm actually a pretty good sleuth about that stuff, so I don't want to do it, all right? So don't copy each other's work. I don't have a policy for makeup assignments, okay? I don't have to take late assignments. Sometimes I have a policy for it, at which point I'd apply it to everyone equally, but it's very important that you submit your assignments on time, okay? And do not underestimate the homeworks. I mean, there's no traditional exams, but the homeworks, I'd recommend working on them early to make sure you get them in on time, because they can be deceptively a bit of time. Who here does any kind of research? Undergrad, graduate? A couple folks do research? Yeah, great, awesome. Sometimes you're on a research project that has a very specific deadline. In my field, happens all the time. My deadlines are typically 3 a.m. on a Friday for some reason. I don't set the deadlines, right? So we're like, some of my grad students are working up to the last minute to make sure those papers are perfect. And so as a result, you have deadlines, right? That's a reasonable reason for an extension. All I need is a note from your research advisor saying, oh my gosh, I need Cricket Skipper on my project. I need them. I need them to do this. Can I get an extension assignment? Sure. Okay. I have that available to you all. All right. So further, Zoom lectures will be recorded and posted on Canvas, and also this lecture. Okay. All these lectures will be posted. Okay. Homework, big deal, 45% of your grade. So again, when the assignment comes out, I recommend getting started. Don't be like, oh, it's due 2 weeks from now, I'll start next week. Don't do that. Okay. And specifically because it's a coding assignment, things go wrong, and you need time to debug it. And you want to go to the office hours and ask us to help you. You want to have that available to you. I just can't recommend that enough. So drop off in an online Dropbox. It'll be Canvas. There will be a Canvas assignment you can drop off your files to. Okay. Typically, I assign it at least 2 weeks in advance. Okay. There's a very specific formatting requirements, and that's really important because there are a few of you. And we need a good way to grade all of them. So if you all submit things in different formats, it's terrible for us. And we're going to start docking points if people don't submit it in the very specific format that we ask for, okay? It asks for PDF, submit it in PDF. If it asks you to format it this way, format it this way, okay? Please, all right? And again, it's heavily coding-based. So you will be doing a lot of coding. This is an applied course. This is an applied optimal controls course. So I want you applying it in code. All right, quizzes. Non-traditional quiz. It's a Canvas quiz. Will be announced, multiple choice. When they're going to happen, we will announce them. Typically, we get at least several days to complete these multiple choice quizzes. And really, the goal is to make sure that you are capturing the core concepts of the class. Okay, that's what the goal of those are. All right. Now, one thing is interesting. This is a hybrid course. Okay. All right. So you're face to face here with me today, right? But because this course is so coding focused, I actually find it's easier to deliver a lot of the material when I am coding in my home studio and streaming it more successfully than today, it seems, to you all, right? And you can join, and you just join via a Zoom link. Now, I can still take questions. I still have headphones. I can talk back to you and stuff, and then the video gets posted afterwards. But Tuesdays, here. Thursdays, remote. So basically, that means we're coding every other lecture together, and you can follow along and code with me. Okay? We will be coding, and you will be following along. We will be debugging together. I will sometimes make mistakes, shocking, but you will learn the debugging process in the process. All right? So video recordings and live streams. I always record these lectures, and and theoretically live stream these things. I don't know what happened today. I was up till 11:50 last night here debugging the live stream, and now it's not working. It's not up, right?
No.
Such is technology. So we'll post it after. So again, no exams. There is no final exam. But there is a group project, okay? All right? So roughly 2 to 3 people, okay? More details to come, as to exactly how we're going to pair up all these people. This is a fairly large class this year. This is a very ambitious project that a student did in one of my very first classes I taught here. What he made is a magnetic levitating light bulb. So basically, this light bulb is powered by the electromagnet that is actually keeping it in place, right? And this is a control system that he put together to make it levitate like this. Very cool. You don't have to do anything physical hardware, physical device like that. That's just a really cool one. I love showing it every year that Fernando made. It's Fernando Ziganov's project. But really what you want to do is come up with some interesting problem, some kind of thing you want to control. Okay? And you're going to use tools from the course to control it. Maybe you only need to do it in a computer simulation. All right? You don't have to do it, make a physical robot. You don't have to make a physical power plant, obviously. But you have to be able to make a computer simulation, something we'll learn to do in class, and then you have to control it. Okay? 2 to 3 people. There will be a proposal component where you propose to me what you want to do. Then you'll have a draft component, which is to show me that you can simulate the system that you want to simulate. Your final report and a final presentation. Okay? Now, to be clear, the final presentations we will submit via video recording. Okay? There are probably too many people for everyone to present in one class, so we'll submit an actual video file. Okay? But they are due at the very end of final exam week. Okay? That's what we're going to do this year. Okay? So there's more details. Who here is a grad student taking it for grad credit? A lot of you, right? Okay. For grad students, what that means for this class, it means you're going to have extra homework problems that are going to be harder. Okay? And you're going to have more requirements on your component of the final project that needs to be yours. Okay? That's the key difference for graduate students. All right. Any questions so far? Yes?
Are there scenarios where we could apply our controls project to senior design?
Oh, thanks for asking that question. I forgot to say it. Yes. The short answer, the question was, can you apply your project to something you're doing for some other project or even for some other class? Yes. If you're doing research and you're like, you know what, I want to apply this to my research. Yes, I want that. I want you to apply it, okay? All right? So that is totally fine, okay? And so I want to see how you apply it to these systems. You don't have to, but I find it's handy. Some of my favorite things I've done as research started as class projects. Okay? All right. So, any other questions? All right. You all seem very excited. Let's keep going here. So, a little bit more about me. So, I'm a robotics guy. My research lab does robotics. My PhD this is sort of a vignette of what I did during my PhD and early postdoc. I do robots that walk on legs. This was some of my earlier work here. I like making robots that walk on 2 legs, that study ostriches, how they move. We built this crazy robot in the corner that could walk and run. Lots of fun stuff. I do it because I like it, okay? And in the lab now, we have this robot Digit. It's like right down the hall is this humanoid robot that we have stepping over obstacles. It is balancing itself. It's doing all the stepping. You can see there's a little obstacle on the ground right there that it steps over, okay? Now, what makes all of these things, what do they all have in common other than they have legs, okay? The thing that they have in common is we used optimal control to either control or analyze them, okay? At my heart of hearts, I love optimal control, okay? Now, there's 2 words there, optimal and control. So what does optimal mean? Anybody? Anybody? Optimization, optimal. Who's heard the word optimal in their lives? Okay. Does anyone have any semblance of what that means? Yes.
Like progressively making something better.
Like progressively making something better. Yes. If something is optimal, you can just say it's the best. Oh, that's the best thing. Or the best thing I can find, right? Optimization is the process of finding something that's the best, okay? And control. Now, control means a lot of things. Anyone want to give me a guess as to what they think control means? Maybe someone who took control last year. Yes?
Using feedback to take in variables and change the output of a system.
Using feedback to take in variables and change the output of a system. That's a very specific definition of control, which I will accept. Thank you, Marco. Anyone else? Anyone take Dr. Higgins' class last semester? In control? A couple of you. Oh, really? So that's great. She taught control. Really cool. She does a great job. And basically, it's the thing that it's something that it's like a decision that you make to get an outcome that you want in the big general sense. We'll talk more about control later, okay? But this course is about controlling something in the best way you can, right? That's what this is about. And that's what all those different robots have in common, all right? And it applies to much more than robots, and we'll get to that in a second, okay? But here's some of the tools that we will talk about in the course. Like, what are the kinds of things you will actually do? Well, here's this thing is called trajectory optimization. People know trajectories, like a trajectory of a spacecraft, okay? Knowing how you would land on Mars. That is an example of a trajectory optimization problem. But you use it for all kinds of control. So for instance, we had this robot here, this purple robot that we didn't have money for arms. Well, no, we didn't have time for arms. We were on a deadline. But we had legs. So I care about the legs anyway. That's my field. I do legged robotics, right? And this was a crazy complicated robot. And this was about 10 years ago now. My goodness, 2016 is when we first started working on this. And we were tasked with making this robot walk as efficiently as possible. The most efficient, the best efficiency control, and to make it walk. Now, this robot had a bunch of motors. It could fall side to side. So what we did is we set up an optimization to figure out what is the most efficient way to get this to put one foot in front of the other. And we ran it through an algorithm that did an optimization, okay? And it came out with these little trajectories for how all the different motors move. And then when you put it on the robot with a little bit of elbow grease, eventually it walks, okay? All right? So, and funnily enough, this particular robot, when it walked as efficiently as possible, it walked like a little bit like a person. I mean, I'm sure you're probably asking yourselves where you find robot shoes. And the answer is at the shoe store. Like anyone else, we actually unbolted the robot foot and took it to the shoe store, size 14 men's. This guy was such a professional, he was unfazed by the robot foot he was sizing. Those Journeys folk, they don't mess around, okay? All right, so it's useful for robot control, but it's not just for robot control. What's chemotherapy? Anyone know what that is? Yeah, someone tell me. What's chemotherapy? Cancer treatment. Thank you. Thank you. So cancer treatment, right? Well, it's important to, on a robot, efficiency is important because you have a battery pack that'll run dry, right? And chemotherapy is a poison that you put in someone's body. But the reason that it's a treatment is because it's more poisonous to cancer than it is to you. But that doesn't mean you can take as much of this poison as possible, right? You want to use as little as you can while you get rid of the cancer, right? So people used optimal control for drug scheduling for chemotherapy. There's this entire field about this, okay? And it might sound very complicated. How would you do such a thing? Well, you'll find out because this is homework 1, okay? I'll give you a problem. I'll give you the equations. And I'm going to say, hey, we're going to simulate how this cancer drug is going to affect these cancer tumors, right? And I'll give the equations, and we will go through how to simulate systems like this. So maybe it's not as complicated as you might assume. Now, that kind of equation, there's a word for that kind of equation. Rhymes with schmifferential. Anybody? Nobody? Differential? Different, yes, correct. How'd you know? Differential equation, right? Now, who took a course in differential equations? Anybody? No. Great, awesome. A lot of that you won't use for this, but it's okay. Some of it you will, all right? So a lot of differential equations is solving differential equations by hand, you know. Anyone remember methods of it, like by inspection and things like that? Very useful, super useful tools. In this class, we use computers to solve differential equations approximately. We'll get into more of that later, but that's differential equation. That's 2 differential equations. So we give you the differential equations. We're going to simulate it. So not too crazy, right? It's homework 1 after all, you know. But just so you think, so another thing that you can do with optimal trajectory optimization, this is sort of a classic problem. This is a pendulum on a cart. Let's run that back one more time, okay? Basically, it's just a cart that you push back and forth, but attached to it is just a swinging pendulum, okay? And it's often a question of like, so a classic trajectory optimization problem is how do you shake this pendulum around, this cart around, so the pendulum goes to the top, and stays at the top, right? It's sort of it's a test bed problem, if you will, okay? Homework 1, okay? Now, you'll be simulating it. I will give you the controller that does that. You don't have to go, I will give you everything you need, but you have to code up a simulation and put it in, right? Okay? So That's what we'll be covering there. Another method other than trajectory optimization is model predictive control. Okay, and to demonstrate this, I need a volunteer that's willing to get in front of the camera. Anybody? Nobody? Marco, you're up. Okay, sorry. Yeah, Marco, you're first. You're first. You're a split second faster. Come on, give Marco a hand, please. Marco, a hand. Let's see. See if I can get this here. Change the scene. Boop, boop, boop. Okay, all right. Hello, Marco.
Hello.
Good to see you again.
Good to see you.
Marco was in my controls class when I taught controls. Controls 1. So, Marco. Okay. All right. You can walk, correct?
Yes.
Great. Awesome. That's exactly the skill that I need for this. Okay. All right. So what I want you to do is to plan in your mind. You're in a way optimizing a trajectory, if you will, of how you would get from there to there.
Okay.
Okay. You have that in your mind. Do you need another minute? Okay. You got it. Okay. All right. So what are you thinking? Maybe 3 steps or so? What do you think?
Yeah.
3 steps. Okay.
Few steps.
Okay. All right. I want you to take one of those steps, if you could, please. All right. Cool. You're good. All right. So let's stop there. All right. So you still have that goal of getting there. All right. Okay. Now I want you to think about how you're going to get there, except now I'm here.
Go around you, probably.
I appreciate that. Thank you very much, Mark. All right. Okay. All right. Let's take the next step, if you could.
Okay.
Okay. Stop. You well balanced? We don't want any injuries on the first lecture.
I'm good.
Save that for the 3rd lecture.
Okay.
Okay? All right. Make a new plan, except I'm here.
All right.
Okay?
Go around you again.
Going around again? I appreciate that again. All right? Okay? Keep going. All right. Now you can finish the trajectory. All right. Thank you very much, Marco. Thank you. We're giving a round of applause. So Marco was doing that trajectory optimization. He was planning over and over and over again. And if something got in his way and if something is changing, he was able to change his plan. Okay? We call this model predictive control because in his head, he had what we call a model of reality. He's walking. There's a weird professor in his way. He has to get somewhere, right? And he's trying to predict where he's going to go, but he keeps changing it as things come at him, right? We call that a feedback controller, okay? And okay, feedback controller. All right. Now we can actually do this pretty well in robotics. Here is Marco, but a robot, and here's very fast me coming at him. Okay. This we did in the lab down the hallway. This is using model predictive control and saying, stay in the middle of the screen. We throw a pendulum at it over and over again. And it is doing that fast planning 100 times a second, roughly. Okay? So it can, as a result, get out of the way. Okay? And this is a technique that we will cover in the class. And it's not just simple little drones. Drones are actually pretty simple. Okay, I shouldn't say that. DJ made this happen. I won't say it was simple. It was very complicated. Okay, the DJ did this in the back there, so he's a pro at this. It's comparatively simple to like a legged robot to do this. Okay, so this is not my work. This was work done at MIT with the MIT Cheetah, where they use model predictive control to make it jump around, step around. So it's a very powerful technique, okay, for optimal control. Okay, but it's actually this technique was not invented by robotics people. In fact, very few of these techniques were invented by robotics people. They were invented by chemical engineers. You know, the reason being is that the calculations back in the day to do that planning that Marco was doing were pretty slow. It would take minutes, maybe hours to do. Well, guess what also takes hours? Mixing chemicals in a plant. So they use model predictive control to adjust the flow rate of a chemical into a plant. Okay? All right, to mix things together. So thanks to chemical engineers. The only time I'll be thanking chemical engineers this semester. Okay. Also, there are techniques like operational space control. It's a pretty advanced technique, and we use it for things like controlling this robot here. This is Cassie. This was one of the first robots we had in the lab here. It's an ostrich-like robot, currently retired, but you can still see it in the lab. And what it is constantly doing is taking all those different joints, okay, and then we tell it where we want the body to be. And it has to, and the controller has to translate how all these different joints can collaborate to move the body in a particular place. Okay. Lastly, there's something that's very hot right now. But it's not a new concept. It's called reinforcement learning. Okay. Reinforcement learning. And the idea is that you define something where you want to reward a controller for doing something good, and then an algorithm will try to improve the controller until it does even better and better and better to maximize that reward. And just because I'm a legged robotics guy, this has actually become a really powerful tool. It's particularly in quadrupedal robots, more recently in bipeds. This is the Animal robot. It was built in Switzerland at the ETH. This is one of the first groups that really showed that reinforcement learning, wow, it's a many decades old concept, could actually work in robots. Okay. Now, we won't be able to go super deep into reinforcement learning, but we can at least give you the basic concepts in this class for how it works. Okay. And the way it works, though, is you create a computer simulation. We're doing a lot of that in the class. This is a very sophisticated computer simulation. We won't code this one from scratch. We'll do simpler ones. But then you do iteration after iteration after iteration to try to improve the robot and to improve the control so it maximizes this reward. Okay? All right. So anyway, and the cool thing is that in spite of all these fancy algorithms, all right, there are at its core these things at the bottom, they're called block diagrams. Let's take a look at this right here. Who took controls before this? What's that? Does anyone know what PD controller stands for? Anybody? Proportional derivative control, right? Despite all the sophistication and crazy computations, this is actually a pretty simple, at its core, that uses some very simple components, okay? Just want to point that out. Okay, now the actual lecture. You're like, that wasn't the lecture? I'm sorry, we're still going, okay? All right, let's give you some more context here, so that way you know what you're getting yourself into, okay? All right, so okay, all of this work. I still have to click buttons. Okay, so 2026 01 08. Okay, we're in applied optimal control. Because I want to show you at least a little bit of math. Okay. Otherwise, I couldn't live with myself before we left today. Okay? So there are two parts of this. There is the control and the optimal part. Now, when it comes to control, what you typically might think of for control for robots, so actually what people think of when they think of control, what comes to mind? Someone who hasn't taken control. Maybe for a robot, what do you think of? Does anyone think of, yeah, what do you think of?
Like vibrations.
Vibrations, that's usually a good answer. I haven't gotten that one before. A lot of people think of code, okay? And you will be coding, as I've said many, many times, okay? But when controls people think of control, they typically think of something that looks like this, called a block diagram, where you have some input, you have a controller, which decides some output. That's a block diagram. It has blocks, it has signals going in, and signals going out. That's what the arrows are, okay? And this controller will then control will apply some effort, we'll call it, to a robot. This is from a robotics lecture, or what we'll more generally call a plant, okay? And we'll draw this all out in the board as well, okay? So, and by plant, we don't mean botany, necessarily. We just mean a thing, it's a process. Think of it more like a power plant. A thing comes in, something comes out, all right? And then there's some output, okay? So generally speaking, we have a diagram like this, okay? Where we have, in controls, we have something we want to happen that's desired. And then we send a signal to a controller. And then it applies some effort to the thing, and then something happens, and we see what happens. Here's an example. Who here has ever baked anything in their entire lives? Okay, great, great. Okay, all right. Try to pick someone else who baked something. In the front, you baked something? What did you bake?
Cake.
You baked a cake. Do you remember what temperature the cake required?
Probably 375.
Probably 375. I won't hold you to it, okay? What did you do to get the oven to 375? What did you do? You preheated it. You had a button, you said 375, please, or had a dial that said 375, right? Cool. So that was your desired temperature, right? Okay. All right. Inside of that oven is a sensor that tells you what the actual temperature is, right? Okay. Now, is your house normally 375 degrees? Nor is mine. So as a result, if I were to take that desired value, okay, and subtract it using this little subtraction operator from your actual value, which is less than 375, the difference between those two things would not be 0, right? Some large positive number, right? We call that number desired minus actual. We call it the error. And it's not just the red text that MATLAB gives you, okay? That error is that difference between what you want and what you have. And you take that error and you put it into some controller. Now that controller does not need to be complicated. It literally could be multiply that error by a number. That's simple. And then it applies some effort, which is how much it heats the heating elements in your oven, okay? And it heats up your oven. But all the while it's looping. It's thinking. It's measuring. It's like, okay, after you had your oven on for a little bit, it's a little warmer, right? So what happens to that error? It was big. Now it's smaller. That might mean that your effort is smaller, meaning you're not heating the oven as much. So as you get closer and closer and closer to the temperature that you want, the oven's no longer heating. Okay? So that's what we often think of as a controller in controls. Okay? Just to give you a baseline is what we're talking about. All right? So now this error versus effort here, okay? So basically this effort is some mathematical function of your error. Okay? And what I just, and here's just an example of what it might look like for like a robot arm. This is a robot arm that I just coded up in MATLAB. And it's trying to chase down that little X that I have moving around. The error is the difference in position between where it's at and where it wants to be. So it's like chasing it down with a little controller. Okay? All right. Just this was a fun one. I had it move faster than I turned off the robot arm in the middle. It's like, turn it off, please. Wah! Now turn it back on. Go, come on. Turn it on. Phew! There we go. All right. Yeah. Fun things you can do with coding, right? So back to our board here. So we talk about control. Okay, so control is an effort that is decided by an algorithm. Okay? Very generally, okay? All right? And the idea is that you have some input to a system and you have some output that you want to achieve. So it's an effort decided by an algorithm to achieve a desired output. Okay. All right? That's what control is. Okay? Now there are two broad categories of control. Okay? One is called open loop, where you literally have an effort that goes in to some system. Again, it could be an oven, it could be a robot, it could be a power plant, it could be a chemotherapy patient. Okay. All right. And then you have some output. This effort, where the effort is some input. Okay? So let's just decide that, hey, we're doing a very simple chemotherapy round. It's like, okay, we're going to give you this dosage for a month. Okay? You don't measure anything. You just say, okay, we've already measured everything. We've decided. The doctor said you get this for a month. Actually, maybe it's like if you ever gone to the doctor and got a pill, right? Like it's like, oh, I have allergies. Like, okay, take these allergies for take these pills for a month. Maybe your allergies will be better. Okay. During that month, the doctor is not measuring what's happening to me. Okay. I just send in that input effort, which is a certain dosage of the medication, and things happen. Hopefully, my allergies get better, right? It's open loop because that loop is not closed off, unlike what you saw for that other loop in the PowerPoint presentation where it feeds back. So another thing we call this is feed forward. Feed forward. Sorry, apologies for my iPad handwriting. I'll do better. I was on leave last term, so I'm out of practice. Okay. All right. The other type is closed loop. And this is where you measure and you compare. What's your name again? What's your oven? What's your oven name? Owen. And what's your oven's name? I don't know either. Okay. All right, Owen. Owen's oven. Okay. Where you have some desired signal, it goes into this little circle with an X in the middle. We call it a summing junction, okay? Really, it's just an opportunity to take one number and subtract it from another, okay? I told you the math would be hard in this class, right? Yeah, right, okay. So, okay, and then it goes into what we call a controller, a feedback controller, and then it goes into what we'll call a plant. That's just the physical system. We also call that the system. And, sorry, and that's your actual output, or your output, okay? And then you measure that with some sensor, and it feeds back into here. You give this a little plus, you give this a little negative, indicating that this number comes in positive, this number comes in negative. You subtract them from each other. Okay, thanks for coming to my TED Talk. Okay, all right. Right, that's a closed loop controller, or what we'll often call a feedback controller. What's an advantage of the fact that we have this feedback controller? Can anyone think of anything? You can optimize it, but you can also optimize a feed-forward controller. So that's a good answer. We can do it for both. Yes, in the back, you had a thought.
You can always ensure that you're going towards the thing that you wanted.
Yeah, you could. Yeah, exactly. So you can always make sure you go in the thing that you wanted in case something went wrong. What if Owen was impatient? I would never say this about you. It's hypothetical. Let's say Owen was impatient. He's like, I'm going to go open up the oven now, see if the cake's done. Heat floods out. Temperature drops. Close it back up. Oh, it's colder than I thought. The feedback controller is aware of it. It can correct. Okay? So those are the two main types of control. Open loop, closed loop. We'll call one feed forward because it kind of goes forward through the loop. And the other one is feedback because it feeds back. Right? Okay? All right. Fun little note. We call this negative feedback because the negative is there. Okay? Negative feedback is people talk about that as a bad thing in real life. In control, it's a good thing. Okay? I knew a controls professor whose students said, oh, my controls professor told a joke today why are you so hard on us? And he said, because positive feedback is unstable. And I'll tell you, you laughed more than you should have at that joke, even just a little sniffle. I gave that joke at a Comic-Con convention a couple months ago, and someone guffawed so loud at that joke. I'm like, can you be like my hype man? It was I could not believe how much someone laughed at that little joke. Anyway, so you have open loop and closed loop control. All right, so that's what control is. And often this controller, where you have some effort, which we'll often call U of t, because it changes over time, and t is time, is some function, okay, of the thing that you're measuring currently. Sometimes we try to measure what we call a state, okay? That x of t we'll call a state, okay? All right, so, and sometimes it can be really simple. It can just be, for example, that u of t is just some constant k multiplied by x of t. Boom. What's that called? Anyone took controls 1? Anybody? Yes? It's a proportional controller. Why is it called proportional control? Because it's proportional. Sorry, trick question. Okay, all right. And that letter K, does anyone know what that letter K is called? Rhymes with main? Gain. It's called a gain. Okay? So who talked about optimizing the controller? Someone, was it you? Someone else said optimize the controller. So a lot of optimal control sometimes is coming up with that right gain. Because who gets to decide what that gain is? We do. We get to decide it. Okay? So in controls 1, you have all kinds of tools such as a root locus diagram or a root locus to come up with gains, right? Here you can come up with the gain that best suit your needs, okay? Now it's really vague. What are your needs? We have to define your needs. And that takes us to the optimal part of control, okay? For any time you want to know if something's optimal, you have to decide, well, what's even better? What's better than what says something's better than another thing? Okay? Who likes movies? Nobody likes movies. Okay, some people like movies. You like movies. What was your name again? Annette. What do you like about movies? What are you looking for in a movie?
I guess comedy or drama.
Comedy or drama. Okay? Does anyone have a different opinion on movies that they're looking for? No one likes action movies? No one likes horror? Yes?
I like ones with like convincing worlds.
Convincing worlds. Good world building. I like Pluribus, by the way. I know I was watching Pluribus. I'm a Pluribus fan. Good world building there. Anyway, completely irrelevant to controls. But you've defined things that you like about movies. So if you're looking for a movie that's good for you, it's probably trying to optimize those things to some degree, right? But it's different because you define what you like about movies, okay? And you define in optimization what you want by something we call the cost function. Okay? Okay. And it defines how good a solution is. Okay? If I go to a restaurant, you got to make a decision as to what you want to eat. And there might be a lot of things you care about, right? What's something you care about when you're ordering at a restaurant? Anybody? Anybody? Yes. Steak and potatoes. Okay. What do you when you order steak and potatoes? What do you like about it? What's that thing you said? Yes, I want steak and potatoes because why? Does it taste good? You can say it tastes good. That's okay. It's your favorite food because I'm assuming it tastes good. Can you say it tastes good for me? It tastes great. Thank you. Okay. Exactly. So, does it taste good? That could be part of a cost function, right? So, like, if you define what's a good food, does it taste good? Is there anything else anyone else cares about when they're ordering food? Nobody else. No one orders food. Yes, yes. When it's cooked properly. Okay, all right. So you can tell. Excuse me. I would like that cooked properly, please. I always tell the wait staff that, and they love that. They don't. I don't do that. That's a joke. Cooked properly. Yes.
How much it costs?
How much it costs? The price. Yes.
Texture.
What's that?
Texture.
Texture. Texture. You like the texture. Okay. Well, anyone care about healthy eating? Not me, but anyone else care about healthy eating? Nobody? Yes, you in the back like healthy eating. Sure, thank you. Some people care if it's healthy or not. It's another thing that could be in your cost function, right? So in an optimization, a cost function defines how good something is. Okay? So how good a solution is. Lower is better. Okay? You want a low cost to your solution. So maybe a cost function for eating out at a restaurant is how bad it tastes plus how unhealthy it is. So if you're trying to come up with a solution that minimizes that cost, you come up with something that is both healthy and tasty, right? Okay? So all optimizations have 3 key components, okay? So there are 3 key components to any optimization. To any optimization, okay? One is, what are even the decisions that you're making, okay? In this case, what you're ordering off a menu, okay? What about more of a controls decision? Let's find something I can throw, okay? Okay? I want to throw this marker and I want to hit some spot on the ground there. I got to decide how fast and at what angle I'm going to throw it, right? That's a decision I got to make. Nailed it. Exactly where I wanted it to go. Thank you very much. So those decisions we call decision variables. Okay? What speed? What angle I threw it? Okay. That's one component. And if you put them together, let's say you have decision 1. We'll call it W1. decision 2, W2, dot, 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 up to decision N. N decisions for some arbitrary decision you want to make. If you want to put them all into one big list, in linear algebra, we have a name for that kind of list. It rhymes with Schmechter. Anybody? Vector, yes, very good. Yes, vector. Okay? So decision vector W has W1, W2, da, 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 all the way up to Wn, all in a column. And that's a vector. So it's a decision vector. Okay? Right? So you have decision vector. Okay. By default, vectors in linear algebra are columns, so we'll write it like that. Here's your linear algebra lesson of the day. If it's a row, anyone know how to turn it into a column? Transpose it with a little t. Okay? That way it fits on the page easier, right? Transpose it. There's your linear algebra lesson for the day. You're all linear algebra experts now. Fantastic. Great. All right. Second thing we care about in the optimization. It's what we just talked about. It's the cost function. So and that is the cost function is some function f of your decisions. Okay? So, and it returns a scalar value. Meaning you got to come up with one number that defines how good something is. That's hard to do in real life. Has anyone ever seen Moneyball, the movie, which I guess is now an old movie? You have. There's a scene at the beginning where, so Moneyball is about baseball and using baseball analytics to come up with a better baseball team by trading, blah, blah, blah. Not that important, other than the fact that they had to come up with a single number that defined how good a player was out of all their different skills, and then therefore determine if they were worth trading and paying money for. Okay? There's a line in that movie. It's like, it's all about getting it down to one number. You could call it a cost function. They didn't call it a cost function, but if it did, I'd be very happy. Okay? All right? So it returns a scalar value, and so the optimal decision W yields the lowest possible value. Lowest value of f of W. Okay? Right? Okay. Last thing, third thing, are the constraints. If I go to that restaurant, I want to buy the chicken fajitas, but they cost $10, and I have $9 in my pocket, that's a constraint that I'm not going to be able to break, unless I want to go into debt for my fajitas. I don't love them that much. Okay? So that's a constraint. So these are limits on the values and of W and functions thereof. Sorry, my iPad has a new screen and it loves to not behave in the same way, so I'll blame my handwriting on that. So, all right, and functions thereof. Okay, all right. So meaning that you have some function g of W is less than or equal to 0. This is the general form of a constraint, okay? Any constraint can be written in this form, okay? For instance, if you had a decision which is how much you're going to spend at a restaurant, okay, some amount you're going to spend, S, and you wanted it to, and it has to be less than or equal to $10. I got $10 in my wallet. I don't know what that gets you these days. It won't even get me a Whataburger meal, okay? I can turn it into this form, via the clever use of subtraction. Okay? If I had a constraint that, I really want to impress my date, so I'm going to spend greater than 30 bucks, greater than or equal to 30 bucks, how do I turn that into less than or equal to 0? I say S minus 30 is greater than or equal to 0. How do you flip anyone know how to flip an inequality to make it a less than or equal to 0? Multiply by negative. I'll choose -1 if that's okay. Cool by you? Thank you very much. So you multiply by -1 by both sides, -1 times S minus 30 is now less than or equal to -1 times 0, which mathematicians will tell you is still 0. Okay? And therefore, you'd say that's 30 minus S, right? Hey, it's less than or equal to 0. Let's say I have a weird peculiarity that I like to have the exact amount of money in my bank account after I have a meal. I want to spend exactly $12.50 on this meal. How do I turn that into an inequality constraint? Even though I say I want it to be exactly that number. So if I want something to be equal to 12.5, I could write it as S must be less than or equal to 12.5 and greater than or equal to 12.5. Therefore, what must it be? Equal to 12.5. Yes, exactly, equal to 12.5, right? And you can write that greater than or equal to now be minus S is less than or equal to minus 12.5. Okay, and then you can put that on the other side, and this is minus S plus 12.5 is less than or equal to 0. So you can write any constraint in the form as being some function of W is less than or equal to 0. And you can have multiple constraints. So this can return multiple numbers in a list, which we have a name for in math and linear algebra. What was it? Vector, right? So it can return a vector. It can have multiple constraints. So what are your 3 components of an optimization problem? Anybody? What's one of them? Cost function. What's another one? Decision variable. What's another one? Constraints. Those are the 3 things. Okay. So what we're going to be doing a lot of in this class, when we're setting up an optimization problem, it's like, okay, well, what are decisions? What's your cost function? What's your constraints? When we were all working on that big robot that had to walk efficiently, what do you think our cost function was? Anyone want to guess? Power, energy cost. Yeah, energy cost. We had a constraint. We had to put constraints because the easiest way to minimize energy cost of your robot is to turn it off. Really easy, right? Not a useful solution. Okay? So we had to put constraints on it and say, okay, yes, you want to minimize the amount of energy that you use, but you have to be at least traveling so fast, at least a certain speed. Okay? In fact, and if you do that, it'll say, great. Falls on the ground, right? Falls on the ground, right? So then we said, okay, all right, now make sure that you start and end at the same speed, right? So we added an equality constraint saying speed at the beginning must equal speed at the end. Great, cool. Now, then it would do things like it would start in one pose, then end in some other weird pose. And we couldn't loop that into a walking cycle, what we call a walking gait. Said, okay, well, you need to start and end at the same pose. And that wasn't enough. It's like, okay, we have to make sure not only start and end at the same pose, all of the joints need to be moving at the same speed at the beginning and at the end. Okay? And you do all that, and you shove it through an algorithm that you can just run in MATLAB, and it gives you an answer. Okay? So much of optimal control and optimization in general isn't even necessarily the optimizing part. It's asking the right question. What am I trying to minimize? My cost. What are my decisions? My decision vector. What are my constraints? The things I can't do. Okay? And that's what so much of this class is about. And with that, I'll leave you there. Thank you so much for coming, and I appreciate it. Look forward to a good semester.